EDX Core Pure, Calculus, Volumes of Revolution, Rotation about the x-axis. We've previously seen how we can estimate the volume generated by rotating a curve fully about the x-axis by breaking it up into equal width discs or cylinders. So here we had discs of width delta x, and we saw that if we made delta x much smaller, so here delta x is much closer to 0, we get a much better approximation for the volume generated. So if we look at this situation where we have the curve y equals f of x rotated fully around the x-axis between x equals a and x equals b. So the region of the curve y equals f of x from a to b is rotated 360 degrees around the x-axis to create the solid. And what we need to look at is a formula to finding the volume generated. So first, if we look at that point on the curve, which is the point x, y, and we look at this thin disk, which is just delta x across, we can look at the volume of a disk, or cylinder if you prefer. So the disk volume for that one disk is pi, its radius is y, so it's pi y squared, and its thickness is delta x. And if we had lots of those disks lined up, all of width delta x, we get the total volume of all those disks would be the sum of pi y squared delta x from A to B. But we want the volume, the exact volume underneath that curve, and we get that exact volume, which I'm going to call V, by looking at the limit as delta x tends to 0. So we're going to have more and more disks all getting thinner and thinner, and we're going to look at the limit as delta x tends to 0 of the sum of all these disks starting at A, finishing at B. And when delta x does get to 0, we get the volume is the integral of pi y squared, and it becomes a dx from x equals A to x equals B. So that's our formula for the volume of revolution when we rotate a curve about the x-axis. That's a full rotation about the x-axis. So there's our y and delta x. There's delta v, the volume of one thin disk. And the volume we're looking for is the sum of all those disks. And as the volume gets more and more accurate as delta x tends to 0, we get the volume is pi y squared dx from x equals A to x equals B. So here we have an example. Find the volume of the solid formed when the curve y equals x cubed is rotated around the x-axis between x equals 2 and x equals 3. So visually, just to try and show you what this looks like, I'll show you a better illustration in a moment. So that point is going to spin around the x-axis, and that point will spin around the x-axis. So you end up with something looking roughly like that. So it's like a solid trumpet shape. Okay, so using our formula, we know we can quote our formula. The volume is exactly the integral of pi y squared dx from x equals A to x equals B. So this volume is the integral of pi. Pi I'm going to put outside the integral as a constant. We know that y is x cubed, so we need an x cubed, and don't forget it's y squared, so it's x cubed squared dx, going from x equals 2 to x equals 3. So that's pi, the integral of x to the 6 dx from 2 to 3, which is pi, integrating x to the 6 is a 7th, x to the 7, from 2 to 3 and subbing in both limits. So the top limit gives me, taking the 7th out as a confactor, so we'll have 3 to the 7, take away putting the bottom limit in, 2 to the 7, so the volume of revolution is exactly 2059 over 7 pi. That's the exact volume of revolution using that formula. So there's a much neater illustration of what's the volume we're looking for. And so using the formula, subbing in for y and subbing in for the limits 2, 3, then simplifying the integral, doing the integration inside square brackets with limits 2 and 3, and then we can calculate the volume from that. So in the next session we're going to be rotating a curve about the y-axis.